You're listening to The Local Maximum, episode 218.
Time to expand your perspective. Welcome to The Local Maximum. Now, here's your host, Max Sklar.
Welcome, everyone. Welcome. You have reached another Local Maximum. Aaron, I am really excited today because, I know this is not the kind of announcement that would get most people going, but like...
Don't undersell yourself here.
Okay. This is very exciting for me because I've been working on this for years. Academic paper, brand new one, right here, out into the public.
Hot off the press. And you have no idea how long it took me to do this. Well, let's dive right in because before we get to the meat and meat and potatoes, the meat of the discussion on this.
Yeah.
Is this in fact the same paper that you mentioned in episode 193 when you announced that you were departing from Foursquare and your list of things that you're going to be accomplishing on your so check that one off.
Okay. I was just. I was thinking 193. That's kind of a long time ago. No, but so that was when I left Foursquare. Okay, so that was October. Great. Started in October, worked on it October, November. Then I was distracted for obvious reasons. Came back to it. Okay, and it was also a lot harder than I thought.
So here's the thing. In the cutthroat environment of pursuing tenure at local Max University, you publish or perish. So you got to stay on top of this.
Yeah, exactly. I know it's. I wrote Local Maximum Labs on there. Am I allowed to do that? I don't know. I did it. So what are you going to do? I'm not part of Foursquare Labs anymore. I have no affiliation. I have no interest in going through all the hoops. I just have something to say. And the thing I have to say is to the data science, machine learning community. So I want to speak directly to them. And I don't know. I'll let my arguments stand on their own merits, I guess.
It sounds legit to me. I mean, it's a division of Local Max Radio Incorporated.
Right. So, does that mean that like if I upload this to ResearchGate or it's uploaded to Archive, if this is there, can I say like this is my official affiliation and I have an affiliation? Or are they going to be like, I'm a little questioning this, but maybe they won't. Maybe they'll just be, hey, that's official. Why not?
Yeah, I don't know enough about publishing in the academic world to know whether that would be an issue, but there are certainly plenty of businesses whose address of record is a post box in Maryland. So this seems no less contrived than that for sure.
Also, Foursquare Labs was just, we worked at the company and we put papers out, so we just wrote it. But like, it's not like they were accredited with anything. So it's the same thing here.
Yeah, I know my company has a labs group, which is where they're doing kind of the quote unquote cutting edge research. But I couldn't tell you much about how that's legally and or academically structured in a formal sense.
I don't think it works as. I don't think it's. I don't.
You don't have to be accredited.
I don't think it's as top down as we think it is. I think you could. I think a lot of this stuff, especially what we're doing here, is. It could be on the basis of your arguments, which I hope I've laid out the story pretty well and pretty straightforward here.
Well, in true fashion, we have already gone off on a odd tangent.
That is
of minimal relevance to the subject at hand.
Yeah,
here.
I've got to apologize to the audience. Okay, keep going. Let's talk about the actual paper.
So the paper itself, it is sampling bias correction for supervised machine learning, a Bayesian inference approach with practical applications.
Yeah. So that's a handful, a mouthful. That's what we get for doing these at 1 a.m. So, you want me to break it down a little bit?
Yeah. So we can dive into the abstract in a minute, but yeah, let's dissect that title for a second.
Okay. Supervised machine learning is, I think, the largest branch of machine. Well, I don't know. It's definitely the first branch of machine learning that you're that you're exposed to in any textbook and stuff. And basically, what supervised machine learning is I want to learn a function. I'm giving you an input, you give me an output, and as I say in the paper, usually I write some code to do that. But now it's like I want the machine to learn how to get input from the output. So whether it's some math thing that I want the machine to learn, or whether it's I want it to learn to give me back strings or labels, like I want it to learn to label images or something like that. I want it to learn to give me the correct response to a problem for some small set of problems. And so what supervised machine learning is that you give it a bunch of examples, and it uses those examples to pick to pick a function, to pick a calculation that solves the problem that it thinks fits those examples best. And then that's your model. And then it has learned that this is going to work given the data that you need.
So to grossly oversimplify this, it's like a much fancier version of when you plot your data from an experiment in middle school physics or chemistry lab in Excel, and then you tell it to solve for a trend line. And so it's taking your data in, and it's coming up with an equation that fits that data and describes it. And obviously, much more complex types of data sets that you're looking at here, but same basic principle.
Yeah, and so in that case, the set of solutions are linear functions. You're only considering those, but there are a lot of them. There are an infinite number of them that you can select. And so it looks at your data, which is like points, I guess, in your chemistry experiment, and it says, okay, here are the lines that I think best fit those points. If you want to look at it another way, I think a great way to look at it was given by Sophie Carr in episode 105, when she said Bayesian inference is like a giant game of Guess Who. And I kind of extended that to probabilistic Guess Who, where it's like if you look at the line of best fit, if you see some of those points, some of those lines get completely eliminated, and other lines are like, oh, okay, maybe that's not so bad. So that's sort of how it does it. And it's got to search that space to find a really good solution. Sort of like we were searching that space in episode 4 when we were solving that cipher that you were building for me. So, okay, that's supervised machine learning. I think we got that down. We haven't really been explaining these things for a while, so it's good to get back into it. So what is sampling bias now? Okay, so I'm giving you data that you have to learn from, but what if I've removed some of the data? What if it's like, it doesn't look like the data that you're going to interact with in the real world because there's a bias. Some of it's been removed, or it could just be that like, hey, the data I have and the data that I'm going to, and the conditions that I'm going to be interacting with in the real world are just different. Okay? And so that could be a problem. In fact, I mean, look, it's always true, almost always true, that the data that you're training on and the data that the conditions that you're going to use your model on in the real world have some difference, some subtle difference, usually. And sometimes it's not a problem at all. But in this case, we're looking at a problem where like a whole class of data points has been taken out, and it's not necessarily, they haven't been taken out evenly. It's not like I randomly removed 10% of the data, because then you're still learning the same thing. You just have less to learn from. But like, what if I took out 10%, but I focused it on certain, in certain areas, like certain points on that line, and so you might learn a different trend line, for example. So that's bias. That's sampling bias.
To those who've followed us in some of the back catalog episodes, we've talked about bias before to some extent. Yeah. But just to make clear that we're not necessarily talking about the type of bias that is often discussed in a sociological or political context in the modern day. Although you often do hear about people talking about bias in AI intersecting with that kind of bias. So we're not talking about necessarily racial bias or gender bias. This is, although it could be the case that part of the problem is I think you mentioned in the paper somewhere that could be applicable to medical data, for example. That maybe you did a medical study and there's lots of data on a particular procedure, but it was done at a hospital in New York City, which has a certain distribution of ethnicities and income levels, which may not match if you were to try and apply the results of the study to a hospital in Texas.
Sure. Yes.
So you may have biased data in that case, or maybe for whatever reason a certain group of that study population was then removed from the study for. I can't come up with a good hypothetical there, but some of the data was excised, and about that.
Okay, yeah. What if? Right. I mean, what if some people? Let's say it's a medical thing, and whether you allow your results to be used depend on what your results were, or something. That could have happened.
Would this be an applicable use case? So I know,
but that's
GDPR has become a big deal in the last. Has it been a decade already? I don't know how far back that goes, but maybe more like 5 years. Yeah. So you could have a situation where all of your European data has been removed from a sample set, and is that the type of thing that you could compensate for with this type of approach? Right.
So it's interesting how you talk about this different senses of the word bias. I think we're talking about the same word. I think the bias that I'm using here is the same type of bias that you talk about in the social political sense. We're just looking at maybe a different aspect of it. And so, yes, I think the idea is so. The idea is this: it's that you can correct if you know what data has been removed. You can correct for it, and I go through the argument on how to do it from a Bayesian sense, and it turns out from first principles, you can come up with a formula to rederive what you can learn on the original data set. Now, so there's some caveats.
I want you to explain more about how that gets done, but before we go there, so you mentioned that if you know what was removed or how the data was sampled. What if you have limited knowledge on that? Like how comprehensive does your understanding of the sampling or the bias have to be for this approach to be applicable? Right.
So this paper assumes that you have the sampling function. So you
don't necessarily have the original data, but you know what algorithm or function was used to sample from the original data.
And it focuses on only a specific class of sampling functions. So that class of sampling functions is that the probability of inclusion is based on what the data is. So there could be a function from input. You could use the input or the output. And so you could have a function from that to a probability of inclusion. And so if you have a sampling function like that to model it, then you can apply this method. And again, I think that's the best way to describe it. Again, this is what's interesting about this show is I think we're doing like a first pass of explaining this in audio, and so maybe I'll do a little lecture on it, and I'll be better at it. But I think this is good. I think now the question is, okay, there's some things in like future work on what if you want to sample differently, right? And then also it's like, okay, well, what if I don't have the sampling function at all? And that is that's going to be a lot more difficult. So I suppose what you could do is if you can kind of imagine what the sampling function might be and then use this technique and then see what you get. And so you can kind of like play around with it. This gives you a tool that allows you to play around with it. But that case is going to require a lot more thinking. I'm not solving all of our problems here.
So is the general concept as simple as if you have the resulting data set and you have the function that was used to sample from the original data set, that you can kind of run it in reverse through the function and get a not necessarily identical to the original data set, but you can get something that is comparable to it? Or is there a nuance in there that I'm glancing over, which makes this far more complex?
Yes. So when you lose data, your results will degrade. Now, not always. look, let's look at your linear regression example, line of best fit. If you have so many points, if you could have a line of best fit where you just have billions and billions of points, and you could see that line very clearly, and you remove half the data, you remove 99% of the data, that line might still be exactly the same, and that might be fine. And it actually might make no difference. But obviously, if data is scarce, then if you lose data, your results aren't going to be as good. Or in the Bayesian sense, really what it means is you're going to have trouble distinguishing between different models. So if we look at if your model is a line, then now it's like, okay, I don't have a single line that I know is the answer. I have a bunch of lines that kind of all be the answer. So there's no way around it. It
kind of has me thinking back to, and we may have talked about this in the context of GANs and AI, but there was some sort of tool that it would take a photo and it would pixelate it, and then from the highly pixelated version, it would reconstruct what it thinks the original is. And sometimes I think there was an example with taking Obama's photo and it got pixelated and then turned into somebody completely different, and just showing that if you remove enough bits of information, so to speak, from the sample you're looking at, then what you reconstruct is going to be of limited fidelity to the original. But,
right. So what I'm thinking about is a situation like this where, let's say we remove some of the answers. So let's say, and this is good to get into some of the examples. One of the motivating examples is image recognition, right? And so I sort of imagine that you have a bunch of photos of animals. Let's say, to make it easier, there's one animal per photo, and you're trying to classify them as lion or not lion. Okay. And you have a few photos of lions, and you have a lot of photos that are not lions. Now, let's say you remove a lot of the non-lion photos because you're like, that's too much data. Let's remove them. And then you learn on the remaining data, it might start to say hey, this lion thing is really common, when really it isn't. But if you know that those have been sampled out unevenly, then you should be able to work backward and say, okay, actually, lions are not that common because we sampled that out, but we have less data on non-lions than we used to. Another example that I could give that I didn't put here is let's suppose we're stratifying by gender and we have some kind of line of best fit. Here's a good example: a height versus weight line. Try to predict the height on the weight, and I think that's going to be different based on gender. I assume it is, right? Yeah. So I don't know exactly how different it is, but let's suppose that it's filtered in a certain way, but for some reason, let's say with men, tall people tend to be filtered out more, and with women, short people tend to be filtered out more. Just that's how the sampling function worked, for whatever reason. And if that's the case, then it could take that into account for sure. So, but if the amount of data has shrunk so much, it might not really be able to figure out what those lines are. But what I'm doing is getting you the best Bayesian result based on what you know.
So I don't know.
So take out the bias, but it might have a wide, wide variance.
I don't know if there's a term for the type of case that you described with the height weight correlation, but the previous one with line or not line, the sampling case you talked about, it sounded like the bias, at least the primary bias there was a base rate bias, which we talked about before in the context of Bayesian analysis. Which is actually
kind of what I had in mind with this paper, because this originally came up when I was working at Foursquare, and I was trying to predict when people visit a chain like Starbucks. And yes, some people visit Starbucks every day, but in general, for a given person day, we have a lot more examples of people not visiting Starbucks than visiting Starbucks. And then, when you go to places like Home Depot or whatever, it's even more. So, you don't want to train on all those non-visits. So we kind of just threw a lot of them out and then ran it through bias correction, and then it's fine. But bias correction was extremely important in that case because we were measuring the effectiveness of the ad, and we had to be like very precise in order to figure out like, how well that ad actually worked.
So this was part of the attribution work.
Yes.
Okay. Interesting.
Yeah, and actually, I cite our we had a patent on that, and I cited that in the paper. So that's the first citation for that patent. And I'm pretty sure the attribution at Foursquare works completely different now after we merged with Placed, even though this work helped us merge with Placed. But it doesn't matter. That's how it used to work. So and it's a widely applicable thing. So I think it's I think it's worth noting.
So in the abstract, you when you talk about sample bias, the term label imbalance is mentioned. Does that map to one of the things we talked about, or is that an additional category?
Yes. So label imbalance is exactly that. Way more days that I don't visit Disneyland than days when I do visit Disneyland. In the case of lion photos, way more animal photos that are not lions than are lions. A lot of machine learning is trying to, the response is either a 1 or a 0, and the 1 is very rare. You're trying to pick out a rare event. And so you might have lots and lots of data, and sometimes you don't want to remove any examples of those rare events because they're so valuable to learn. Because as the example I give in the paper, once you start taking away lion photos and you have very few left, you really can't learn what a lion is. And you could kind of make an analogy to human learning. Like if you don't have a lot of examples of something, you might not be able to figure out what it is at all. So
we run into major overfitting, underfitting problems.
Yeah.
Another thing we talked about in some of those early episodes.
Yeah. So what you can do is you could remove the negative example, and then you have that label imbalance. It's not so much that you're fixing the label imbalance, although you are, but you're sort of shrinking the data down so that your algorithm can run faster, because a lot of machine learning algorithms either require running through all the data, and several different times, which could be crazy if you're running like a batch algorithm, or even if you're running like a gradient descent algorithm that's stochastic, which means it's taking a small sample of the data at once. You're going to be able to learn a better model faster if you're getting the examples that you need. So you really want to, in many of these cases, kind of just remove all this extraneous data that's sort of useless. I don't think, just the lion, coming back to the lion example, let's say you're trying to teach your kids about lions, right? And you have a book on lions and you have 30 books on elephants. Wouldn't it be better to show them, here's a book on lions and here's a book on elephants, but if you show them like lions and then 30 books of elephants, do you think that would help them learn lion better? Probably not.
Yeah. Probably would be a little bit of overkill.
Yeah, it's the same thing with machine learning. Now, a lot of these algorithms are not going to be hurt by the 30 books of elephants, although as a human probably would. Although some algorithms actually would get hurt by doing that, but I'm assuming they wouldn't. But I'm also assuming that there's a lot of data that's fed into these algorithms that's actually useless in terms of helping the machine learn. And that's kind of an area of future research, which is how do we, and obviously research has been done on this specifically in the field of active learning, but the question is like, how do we figure out what data is useful and what data is useless before we include it in the model and measure that, because that's very expensive.
Yeah, being able to pre-filter that in a less lossy way would be quite useful.
Yeah.
So I had a note here about kind of the conditions where this is particularly useful, or more where the biasing of data is particularly a problem that you're trying to attack there. What were, did you run into any edge cases or particular instances where that motivated this specifically?
Yeah.
And so you talked a little bit about the attribution case, but
that's exactly what it was. Yeah. But when trying to think through the attribution case, and the reason why I found this interesting was because it wasn't at all obvious how to do it. And a lot of people suggested doing an ad hoc method where you train the model first on the bias data, and then afterwards you add a correction term. And it turns out that's the wrong thing to do. The right thing to do is to kind of base it in, bake it into the posterior distribution when you're running Bayesian analysis, and basically, make your adjustments that way. And coming up with the formula for it, again, wasn't obvious. You really had to be very clear in your thinking. And that's what we did when we went to the whiteboard and really figured out what's going on. And this is the result of that. And then we realized, hey, it doesn't just apply in this case, it applies in many other cases. It could apply in case where, because in this case, we bias the data. So we knew how to do it, but it also applies in cases where you know how the data was biased and you weren't the one who did it. And so it could apply across the board. So
something you just mentioned there, and it pops up right in the abstract, is that the way you're doing this is by altering the posterior distribution in your Bayesian inference framework. So
right.
So let's take a minute and refresh our memories on the posterior distribution.
Okay. So these distributions can be thought of as beliefs as to which model is the right one. So in the case of linear regression, as you put out before, you've got a bunch of lines, you got an infinite number, and you want to know a probability distribution over them. And you have a prior. You're like, okay, I think it might be, one of these lines. And so essentially you basically have a big mathematical space of models, and your distribution is, one way to think about it is each one of them is assigned a number. And so that's kind of the relative likelihood of each one. And so it essentially encodes your beliefs over which one is the right one. And we have to assume one is the right one, even though that's not true, but that makes this whole thing possible. So you have you set a prior on everything onto which one is the right one, and which could be, you could use in different prior what's it called? I have the vocab term right here. I've got to go look it up. It's it's an uninformative prior. That means like, hey, I don't know which answer is the right one, so I'm gonna pick a mathematical distribution that is maybe convenient. It's got to be open-minded. Some of these distributions are more open-minded. Some of these distributions are more closed-minded. So that's where you start out with your prior. Then the data comes in. And then from that, you use Bayes' rule to make the posterior, which is your belief among them after you've gathered the data. So if you think about it in terms of guess who, it's another one I like. Prior is all of the cards are up. Posterior is, a bunch of your cards are down. And so, if you think about it, interestingly, if you do kind of a Bayesian version of, linear regression, like fitting a best line, you're not actually eliminating any lines, but some of the lines, their probabilities go exceedingly low, like down to zero. And then other ones kind of go up. Now, if you're fitting some more complicated polynomial and you don't have data all the way out here, then, you're like, well, I don't know if this line is going to go up from here or if it's going to go down from here, right? And so those two, let's say you see things that are like mainly linear till here, but like it's possible it slopes down, it's possible it slopes up after that, you don't know. Those might have similar probability still
that was
after
always
all
the
said and
problem.
done, so they might not eliminate all of them.
That was always the problem messing with best fits in Excel. back in the days, that you can just add more polynomial factors and you'll get a real wiggly line that hits all your points. But once you get outside of the narrow window where you have sampled data, is that line indicative of anything representative at all?
Right. And
so that's a classic overfit.
Yeah, and Bayesian, the Bayesian version of linear regression is kind of different than what we're thinking about. Whereas the Bayesian terms of linear regression it's a line. It's a line, but it's really more of a tunnel where each point in the line has like a normal distribution around it. And so, like, that can widen and shrink depending on, are there points that are really far? Are there points really close in? So there's all sorts of things that you can do with that. But as an example of bias correction, let me give that example again, where you don't know if the line over here slopes up or slopes down. But let's suppose that all of the points that show it sloping down have been removed, and then there are no points, then it'll know it probably slopes down because those have been removed. Or if it sees lines that show it slopes up, but it knows the ones sloping down have been removed, then it might not make a decision. So it's it kind of figures that out. It is what the point of this paper is.
So we've kind of touched on the edges of what's going on here.
I think I need to close the loop there. Okay. Is that the posterior distribution has a formula. It's Bayes' rule. It's a pretty straightforward formula. Posterior distribution is proportional to the likelihood times the prior. Yeah, we don't have to get into that there, but it's a straightforward formula. When you correct for the sampling bias function, it's I think after you read this paper, it's kind of straightforward, but it's actually not as straightforward. And there's kind of a subtle subtle mathematical quirk in it. And so basically this goes into how to derive that. And so now you have your posterior, you have a new posterior to correct for that bias. And posterior is what the learning is based off of. Like if you're trying to learn a model, whether it's like deep learning or whatever, you're searching that space of models and you're looking at the posterior to see, is this good or not? So that's where everything that's where all the learning algorithms base their answers on. So it's great.
I was going to ask if you want to go into the nitty gritty of the math on this, but that's a little out of the scope of what we want to talk about here, and that can be addressed in more detail in a later adventure.
I think there's one interesting part, which is sort of what's it called? It's not a thought experiment. Is it a thought experiment or more of a thought? I feel like there's a word for it. But anyway, in terms of getting the mathematical formula, you kind of have to take that sampling and you think of it as sampling, right? Hey, I'm getting this data and then each one deciding whether it's in the set or not in the set. You kind of, I think the crux of it is kind of this thought experiment on page 7, where we turn it into a generative description of how the data was generated. And it's basically like, okay, we got the input, the model produced the output, then we put it through a sampling function, and the sampling function told us whether it was accepted or not. And then if it wasn't accepted, we went back to the beginning. And so we kind of use this flow chart to create an equation. And it's not just any equation, it's a recursive equation, because part of that whole description is go back to the beginning. So it's like, x equals a bunch of things with x in it. And then you use your algebra to solve that equation for x and get the answer. So that's kind of the crux of it. It's a kind of an interesting way to solve a problem. And I actually think it doesn't take a whole lot of background other than, I feel like it takes calculus to understand the continuous version of this stuff. But if you just want to read it and just look at like the discrete version, you might be able to understand it with just, kind of high school math. So
presumably you guys applied this in work at Foursquare.
Yeah. And this was basically my thing. So I did this.
Was that?
but a lot of people, more people did attribution. So yeah.
And I guess you did this in software in some sense, but
Yeah.
is this this method something that there exists, like, you know, a software package or a plugin that implements it, or if someone wanted to take this paper and use this on their own data sets, they would have to implement it from what you've described here.
Yeah, they'd have to implement it from what we described here. There are a lot of software packages that say, give me the posterior distribution, or give me the log of the posterior distribution, use the minus log of the posterior distribution, and I'll give you the answers. And so, okay, all you have to do is use this technique, put it in your posterior distribution, you should be good to go. So yeah, if anyone out there actually applies that, I definitely want to hear about it. I hope people do. And yeah, I'm sure people have done similar things already, particularly for logistic regression, but this really solves the general problem.
And you mentioned earlier that there's some future work that you outline here. Is that something that you're planning on pursuing in the near future here, or you're more laying out for others who might be interested in exploring in that direction?
Well, I don't know if you remember this, but like there was a time when I was working this and I was like pulling out my hair because like I couldn't solve problems, and I was on the phone with you and you said, "Oh, no. It's okay, Max. Don't worry about it. Just put it in future work and you'll be fine." And so that's what I did. Now, that doesn't mean there's not going to be any future work. And I think that some of these things I might return to. I don't know if they're going to be a full paper like this. It might be a shorter paper that I don't put on archive. I just put on the website as Local Maximum Labs. Or it might be that some of this stuff I don't get to because I'll be onto different things. Yeah, I think there is one problem in future work that really bothers me. Should I tell you? Yeah. So it's the first one, which is simple random sampling. Okay, so I looked at a case where it's like, okay, let's suppose we kept all the positive examples, but we removed 90% of the negative examples, right? This allows us to fix it. But what if instead I say, okay, we're going to take exactly 100,000 positive examples and exactly 100,000 negative examples. And we know what proportion of the full data set each of those is. So the question is, can I just use those numbers? Because what we're doing there is not exactly the same. And I had trouble like proving that mathematically. And I feel like, so I just left it up to future work, but I felt like I should have been able to do it. So yeah, it bothers me. I feel like if you use the same formulas that we developed here for simple random sampling, it would be so close that it would be, that if not exactly correct, it would be indistinguishably correct, would be my guess, but I'm not sure it's exactly correct. I feel like there's some nuance in there where, it's like, okay, what's the probability you picked this exact 100,000, and now you're talking about permutations and something with the math. I was just not quite comfortable saying that it's the same. And so I don't know, maybe someone else can answer that for me, but I wasn't able to answer that question, but I don't think it's an unsolvable question.
Well, certainly be interesting to see if there's any follow-on work referencing this that perhaps nails that down further.
Yeah. Actually, a follow-on work that wasn't mentioned here is actually something surprising that's completely different. Is I talk a lot about proportions here because they're not equations. It's just this function is proportional to this function. That means, if you multiply it by something, they're proportional. And I feel like there's a lot of work that can be done on the notation of proportionality and looking at these proportions and understanding them as well as equations, because I feel like there's actually a lot of nuance there that is kind of specific to machine learning that maybe mathematicians have known about, but haven't the notation is a little clunky. And so I almost want to look at that to a certain degree, because it's an interesting problem. It's there's a lot of interesting nuances there. For example, if you want to look at like a probability space, right? Let's suppose I could have one model that's like infinitely more probable than another, but let's suppose this model is infinitely more probable than two models. Can you compare those two models? In fact, you can assign their comparison anything and it would still be consistent, but you could also say they're uncomparable. There's all sorts of weird things that happen with these probability measures that have to be squared with the actual practice of machine learning. And so I would love to look at that. Now on Archive itself, I'm only allowed to post for machine learning because many years ago somebody endorsed me. In fact, Tassos endorsed me. He was on a past episode. But I don't know how to get the endorsement for math, but maybe someone can do that for me. But no rush because it's going to take me a while to do this. And plus, this is not my only project. Wouldn't it be nice to create a whole lab with like tons of people working and we like pump out a lot of this stuff, but that's not what we have here today.
Not yet.
I mean, yes, we have a few, we have a few people, but
so you mentioned a couple of times that this will be on was it Archive? But what's going to be the easiest way to find this paper, Sampling Bias Correction for Supervised Machine Learning, a Bayesian Inference Approach with Practical Applications? Well,
for right now, let's just keep it at the show notes page because that it will certainly be there before we find the final home for it. So that's going to be localmaxradio.com/218, 218. So that's it. Always point to the show notes page.
Awesome.
All right. I think we got through it. Do you have any more questions about this before we wrap up?
I mean, how does it feel to be done with it?
Oh yeah. Let's just talk about the process of it. So this was really hard to write. I would go through, this happened in October. I started going through like the whole paper and I'd have it all marked up with all sorts of errors. And I'd fix the errors and then I'd print it out again.
And presumably at this point you weren't looking, you weren't finding mathematical errors. Like,
oh yes, I was.
Well, like in the theory was wrong, or just you hadn't explained it clearly.
No, like even as like last week, I was finding like a subscript that I used the wrong letter, things like that. And I'd be like, there's an S sub n in my equation. I never defined S sub n. What is that? It turned out it was X sub n. And somehow I had S and then I copied and pasted it all over the place. And so I was finding those errors. I found grammatical errors, things I wanted to change, things that were unclear. And then you'd print it out again. I'm saying you because you're imagining how crazy this is. And mark it up again. And why am I printing out and marking it up too? That's another interesting question. And then there's the same number of markings, so it like doesn't get better. And it took a really, really, really long time in order to get this to a place where I wanted it. But I wanted it to be well written because this wasn't for to get a PhD. This wasn't, it wasn't like there was a goal to clear some hurdles. It was written because I actually want people to read it. And so that was important to me. And so actually, can I just read the first two paragraphs?
Yeah,
I really like the first two paragraphs.
So this is the introduction?
Yeah. Developing algorithms is a central task in computer science. Each algorithm is a series of precise instructions to compute a given mathematical function f. This works great when the programmer has these precise instructions available, but not when a function is only partially known or if it is too complex for even a large team. Machine learning was developed in part as a response to this problem to extend the ultimate reach of software. And I don't know, I just like that introduction. I feel like, that gives me the that gives me the motivation for why we're doing machine learning. And then I start, as I get forward, I get into more specifics of what type of machine learning I'm talking about here. But I just want it to be fun to read because I also want it to be easy to, you could like skim through to, I don't know what it is, like equation 9 and get the let me make sure that it's actually equation 9. But it's, I looked over this so many times, but it keeps changing the equation number. No, it's not equation 9. Yeah, it's equation 8. log likelihood loss with the sampling function. So basically, it's easy for someone to just use it if they want to, but it's also fun to read. And so that was important to me. And so that's why it took a long time. But but it's like, how often can I do this? I don't know. It was a lot of work. Maybe it gets easier, but it's still kind of hard. Way harder than I expected.
Yeah, and I mean it's what 13 pages including references. So it's not not a massive tome that people won't be able to get through. And it is technical, but it's not written to be completely opaque. So don't let it scare you off. And now you mentioned that you want people to read it to hopefully find ways to use it. Do you have any other plans other than the obvious, talking about it here on the show, to kind of get word out about it, to get some visibility for the paper itself?
Yeah. So I think I'll do a quick blog post. I'll put it up there. We'll have the show. I have it on archive, and I'll probably do a demonstration of it at the board. Another thing about this paper is it actually just turns out to be a really great introduction to machine learning. So if you're curious about machine learning, particularly supervised machine learning, and you want you want to learn it the Bayesian way, then section 3 of this paper just goes through this and you'll know it. And, this is the same, it's kind of it kind of sets up my variables and stuff. And it's the way, this same explanation will appear in a lot of textbooks and things like that. But I thought it came together pretty well. And so I'll probably also do a video of that, maybe, at the whiteboard over here, and we'll start getting some local maximum lectures that are not part of the regularly scheduled podcast, and that'll be exciting. And maybe as part of that, I'll also go into the bias correction section.
Awesome.
So hopefully people watch these videos. I feel like those lecture videos sometimes get more views, but I don't know. I need to figure out on locals and on YouTube and Odyssey how to up those numbers, because the podcast numbers aren't bad, but those, and they're public, so I can't hide from them. 10, 20 people view these videos. So I kind of wish there's more. Maybe it's just people prefer listening to it on the podcast, but I feel like the lectures at the whiteboard, people are going to have to look at the video. So hopefully people are going to be searching for that. And when I did the video 7 years ago or 8 years ago on the Dirichlet distribution, which is the last paper like this that I did, 8 years ago, in 2014 was the last time I published to archive. The paper got a lot of citations, and also the video got a lot of views. Now the video is part of a different channel, so maybe it was the channel, but also I think people were searching for it, and I think this is a more well-written paper. So hopefully this will get more citations as well. There was a guy in his, and some of these citations are funny, like it has nothing to do with what I wrote in the paper. But there was a guy who cited me in his PhD thesis, and he's got a whole section like Sklar says this, Sklar says that, and it's it's amazing. It's pretty fun to read. I might. Maybe I should look up who that is and have him on the local maximum.
Very neat. Yeah, and talking of whiteboard videos, we'll certainly have to explore with a slightly different format there and work out the kinks. But could be some interesting stuff to do with that.
Yeah, it's not going to be how should I put it? I want it to be lightweight on my end. I just want to be able to go up and say some things, and videos are nice. You could skip some parts if I get distracted or whatever. So hopefully I'll be able to make these and not be such a perfectionist about it, because there's a reason why I haven't started. I mean, I guess I haven't started because I'm working on this, but maybe we could do better.
Well, yeah, with that hurdle cleared, then there's potential for some exciting next steps.
All right. Yeah. Sounds good. All right. We are we going to adjourn for the day?
I think so. I'll give you the closing remarks. What any additional takeaways that you want to draw our attention to here?
Yeah. I think that I think there is tremendous value in thinking about machine learning from first principles, and as we've explored on this podcast, there's also tremendous values of talking about machine learning, even if you're not in the field as a person, to just try to understand the world and try to understand, learning in general. So yeah, if you're interested at all in machine learning, give it a read. I think you'll learn a lot. I think it will kind of clarify your thinking a little bit. Maybe you'll disagree with the way I think about it and have your own comments. So I'd love to hear them. So we can, with that, call things to a close. Remember, it's called Sampling Bias Correction for Machine Learning, available now at localmaxradio.com/218. Also, make sure that you go on our locals and join the discussion as well. One member of the locals who's a paying subscriber, and it's not much, it's $4 a month, has said it's the best $4 he ever spent because he has access to us. We talk to people on there all the time. And you could also talk to kind of like-minded people who also listen to the show.
So I was going to ask, and obviously going on the locals is one way that folks could reach out. But if there's feedback specifically on this paper, what is the best way to get in touch with you about that?
You could go to localmaxradio@gmail.com.
Awesome.
That's the best way. So yeah, a second best way. Best way, subscribe to locals. Give it, even for a month. That's the best way. All right, great. So here we have it. Got to fund the research somehow, right? Here we have it. All right. I think we're gonna wrap it up with that, and we're good.
Yeah,
we're good to go.
Yeah, this was fun.
All right, this was very fun. Yes. Have a great week, everyone. That's the show. To support the Local Maximum, sign up for exclusive content and our online community at maximum.locals.com. The Local Maximum is available wherever podcasts are found. If you want to keep up, remember to subscribe on your podcast app. Also, check out the website with show notes and additional materials at localmaxradio.com. If you want to contact me, the host, send an email to localmaxradio@gmail.com. Have a great week.
Feel the power.